Hi, welcome to the Signal Path. In this episode, we're going to try another repair. This is an Agilent E5071C. This is a network analyzer. This one goes to 4.5 gigahertz, but they come in a lot of different configurations and channels and so on. This was kindly sent by Altest. As always, I can just ask them for an instrument, and they have such a huge inventory that they can have both a broken one and a working one available to send in. So I wanted to try a network analyzer, so they kindly sent one, and I've left a link to their website here in the video description if you're interested. So let's see what's going wrong with it. Well, obviously the very first problem is that this one is missing a hard drive. There you go. You can see there's nothing in here. I took the top cover off in anticipation to see what was going on. And this one has the option of a removable hard drive. You can see that you can lock it in place, and this one has obviously been removed. Now this is not a good sign. This typically means that something else must have been wrong with the instrument and they needed the hard drive perhaps for a different repair. So we're going to have to take a close look at it. But I'm going to have to probably borrow an image from a 5071C that I already have in my lab. It's a different model, a different configuration, but that doesn't matter. The operating system is really the same. Well, as always, of course, Pooch is making sure everything's working, and I think he's looking for something inside there. There you go, Pooch. Make sure everything's all good. So here is the interface to the hard drive. Now, this has its own unique connector. That's because you can slide this in and out, of course, and that way you can remove it very easily. But nice, it turns out that at the back we have a connector, just a basic IDE connector. So this little PCB interface isn't really even needed. So if I just get a converter, I should be able to connect the hard drive with the image directly to that. So I'm going to try that first. So here we go. The simplest one I could possibly find is one of these, and I have already taken an image, this hard drive with the image of the 5071. So we should just be able to now unplug this at the back, which is just a basic IDE cable, I believe. If I can get it out. There we go. Yeah, there it is, and I can now simply just connect these to each other, and that should solve the problem. And let's also take a look inside the unit and see what we can see from the top. Alright, here's a look from the top of this instrument, and it is basically based on a simple PC, which is at the very bottom there. I think this is even a standard motherboard. There are some additional cards in there, GPIB and so on. These are the custom ones that Agilent has made at that time in order to interface with the rest of the instrument, which is actually all the way at the bottom. Lots of fans over here, just a basic power supply. Here's the hard drive installed. There's a solid state switch here. This could most likely be for the stimulus switching between channel 1 and channel 2. And I do see that those indeed go to the front end modules for channel 1 and channel 2. Really, there's not much to see here. It's going to be a very basic instrument. And you can see that there is cards essentially at the bottom here. Some of them are populated. And that's how they set the options for this. So depending on how many channels this has, the frequency range, you will have additional things either installed or not installed. I believe this 4.5 gigahertz is probably one of the lower end models because it's a low frequency one. And only had 2 channels, but these things do have TDR options, they have frequency offset tracking, and so on. So these things can in fact be fairly advanced when they're populated with the right options. And check it out, I managed to get it to boot up and install the correct software. After a bit of fiddling, it's finally running. So yeah, it looks okay. You can see that we're measuring S11, but I don't quite like the look of this S11. Right now there is absolutely nothing connected to the connector, and the instrument is not even calibrated. But you would expect essentially full reflection on the port because there's nothing there, and there is some waviness to this, and that doesn't look normal. If I go to S22, you can see that how flat it is, and even without calibration it looks like we are receiving the right amount of signal. So if I go back to S11, yeah, something's unusual. Now this could be a receiver problem, could be a transmitter problem, or maybe just a calibration problem. Either way, let's go ahead and try measuring to see what's coming out of port 1 versus port 2, so we can do some basic tests on how the instrument is operating. So let's go ahead and investigate any asymmetries between port 1 and port 2 of this instrument. I have 2 power sensors connected simultaneously, so we can measure the 2 powers at the same time without moving anything. These are both N192 3A power sensors, extremely precise with their own built-in calibration, so we can be sure that they're very well matched. Right now I have configured the instrument to put out a single tone at 4.5 gigahertz, and we can change the stimulus to go from port 1 to port 2. There's no calibration at all, so we can see the raw power between those two, and we can see the differences between the channels. So right now it's running 3-second sweeps, and we're looking at this, and the power sensor is of course connected to a power meter. Let me span over here so we can see it. So right now I have set the power to be about 10 dBm. There you go. So you can see we're looking at one of the ports, and it's putting out 9.56, and I believe this is port number 2. This is the port that I think is working correctly. You can see every once in a while the power changes up here, and that's because we reached the end of the sweep. But anyway, it's correct. So 9.56 seems like reasonable. Let's go to port 1. And here's exactly the same setting on port 1, and you can see the power is a little bit less. about maybe 26 millidB, 260 millidBm. It's different. It's not really that much, but I still don't think it's working. There are other signs where there is a difference between these two channels. If you look at the screen when they're connected to the power sensor, there's some more clues there. So right now the instrument is not calibrated, and this is the return loss as a function of time at 4.5 gigahertz into the power sensor. You can see that we're measuring about -20. Now remember that the power sensor is connected directly at the connector itself, so the measurement plane is at the connector. Again, there's no calibration. What I'm interested in is the differences between the two channels. So here's S11. You can see we're sitting at -20, which is not that great because these power sensors are designed to absorb as much power as possible inside of them and not reflect anything back into the instrument. And I'm going to do the same thing with S22. Look at that, the difference is considerable, about 20 dB. So yeah, there is a difference inherent between these two channels. And even though it seems like it's okay, I'm still inclined to open the channels to make sure, to see if they're okay, and of course for us to take a look because it will be interesting to see the individual TR modules. Just to show you another frame of reference here, this is a different E5071C. This is a 4-port network analyzer. This is the one in my lab. It goes up to 8.5 gigahertz. And there's no calibration right now. This is factory calibration. The measurement plane is essentially at the edge of these connectors just like before. And if I look at S11, you can see how flat it is. I can look at S22, the same thing. S33 as well as S44, and you can see in all cases we have a fairly flat response despite the fact that the instrument is uncalibrated and the powers match quite well. So therefore I still think something is wrong. Let's go ahead and take a look at it. And here is the front of the instrument with the LCD and everything removed. We can see port 1 and port 2 here and here, and I did manage to find a hard drive enclosure. I had to get it all the way from Korea. This was really hard to find, and I don't think there's actually even any more of them. But anyway, so the two TR modules in the front, you can see they're very narrow and long, and they're obviously not based on couplers. Traditional couplers, they're going to have a different kind of coupler inside. I'm eager to take a look at it. But at the same time, we have our probably main synthesizer here going into a distribution switch, and you can see that the distribution switch has two terminations here. That's because there are the two other channels. This thing can be configured up to 4 channels, but the other two are used. It seems that they go into these ports and then come out of these ports going into a solid state switch, and that's how the port direction is selected, and then that goes back into a down converter. So there's an IF section and synthesizer sections here. I don't think there's anything wrong with these, otherwise we wouldn't get anything from this instrument at all. But we should open this one and take a look and see what is inside, how it's built, what kind of front end does it have, what kind of synthesizer, a forwarding path it has, LO amplifiers and so on. I'm eager to see. And then we also have a reference one to compare with, which is great because this one is indeed working. So let's go and take these out and take a look at them. And one thing I forgot to mention, it's good to point out, you can see there are two identical synthesizer blocks here, and that's because this instrument indeed supports offset tracking, and it can measure down convert mixers and so on. There's a license for that you have to enable, but having two of these identical one going to the TR modules and one going to this down convert here allows you to do all of those offset tracking, mixer, and nonlinear measurements, nonlinear frequency conversion measurements, I should say. So yeah, this can be configured to be pretty powerful with the software that comes with it. Okay, so here's the TR module. I've taken all the screws off. You can see this is the connector back to the motherboard. We have a Spartan FPGA here, probably some glue logic, making sure everything is connected and has a standard interface to the bus, the main motherboard of the instrument. Some DC-DC conversion, voltage regulation going on. Nothing special. I'm going to go ahead and remove this. These things do stick to the PCBs when they've been closed for a long time. There we go. I think it's coming off. And there it is. Look at that. Looks really nice, and it has its own part number. This looks like it's molded. It's not machined. Very nice isolation in all the different pieces. You can see the gasket preventing any EM escaping. Lots of different cuts of RF absorbers in order to make sure there's no cavity effect happening and no internal reflections building up. This is very classic. We've seen this many times before. Two adjustment screws over here for the R and T, the reference and the test channel, which is interesting. And here is the front end. Yeah, it's very barren. There's not that much in there. Looking at this, oh, look at that. Check this out. Let me zoom in here. Look at that. Let me see if this would focus. Come on, go ahead. There it is. Check it out. Yep, I knew there was something wrong with it. Yeah, these resistors are toast. They've experienced quite a lot of power being dissipated in them, and they are totally destroyed. It's interesting looking at this, and there is a DC block here. There's a capacitor here, capacitor here, capacitor here, and the input is of course connected. So there is no DC path that I can see. So it's interesting how this resistor has been destroyed. It must have been destroyed due to an RF event, not to a DC event, which is interesting. I don't think there is any DC path, at least not that I can see. Oh, look at that. There is an area over here which is reserved for a bias T. That's not populated. This is most likely the very first inductor in the bias T, the lowest frequency one. You can see that this path here is not populated, this jumper over here, and there's several components in here, potentially a wire bond or something over here for a DC block might have been here so that the network analyzer can have a bias T at the front end, which of course this one doesn't have. Yeah, so yeah, this is problematic. These resistors are destroyed to a point where I can't see the numbers on them anymore, at least not right now, but we do have a working channel, so we can open that and see exactly the components that are supposed to be here. And let's do some analysis on this, and I'm going to go over the different blocks and tell you how it works. So let's look at the RF portion of these TR modules. Everything on the left of what you're looking at on the screen, all this stuff is just DC and communication and voltage regulators, really nothing that exciting. But we can look at the RF section, and this is the incident signal coming in. There is an attenuator here. This is just to improve isolation, remove any reflections, and just balance the signal out and make it nice and predictable. And then there is a bunch of bow tie filters over there. And that line goes into an amplifier. This is the power supply section of this amplifier, and into another, what appears to be another amplifier, followed into a broadband splitter. This broadband splitter splits the signal into two paths. So we have to transmit, and we have to test and the reference path. And then there are two ICs here. These are the same IC, and they're both Agilent branded. Could be a variable attenuator in this path, could be an amplifier or a programmable gain amplifier. Going into another amplification stage, and again two ICs. These are different ICs than these ones that are also Agilent branded. Interesting that he has one input and two outputs, and the output is connected into a highly resistive coupler with an isolation port terminated there. It's an interesting structure. I wonder what they're doing with this. They could be doing various kind of potentially even phase shifting. They could be doing gain control, amplitude control, and they just have a very good return loss looking back here. Very well behaved impedance from these two couplers. So these two paths are essentially identical, and they can turn them on and off, and respectively depending on whether they want to do the test or the reference incident wave. And then output of that goes into this other board, and this board is obviously separate so that they can configure this for different frequency bands and change them as they see fit. This is all screwed in and now soldered in place with the connectors, so it's going to be difficult to remove. So all the work we're going to have to do on this broken section has to be done while this is inside. And this is based on, appears to be a Wheatstone coupler. Now, Wheatstone couplers and resistor bridges are fairly common in a lot of applications. They're used for measuring an unknown impedance across 2 points, and they're quite really versatile. The use of them in the front end of a network analyzer is also fairly common because the EM-based couplers are fairly large. They definitely don't go down as much in frequency. Their bandwidth at lower end is limited. These Wheatstone couplers and bridges can indeed go down all the way to DC. And the only reason this doesn't go down to DC is really these AC blocks and other reasons for the down conversion stages of the network analyzer. But we can open the other one and see the configuration and essentially replace these resistors. They're still obviously working to some extent, but because they're all charred and the board is damaged, we're going to have to clean them up, and hopefully this would improve things because the original factory calibration is all gone as a result of that. But I'm going to put an article for you to read about Wheatstone resistive bridges and so on. I think if you find it interesting to see how they operate in a network analyzer. So that reference signal coming over here, then you have the reference and test incident stimulus and going into these two paths, and all the reflected signal coming back goes out this way. Now, resistive couplers don't have isolation and directivity the way an EM coupler has, so they inherently reduce the dynamic range of network analyzers in some scenarios, but they have other benefits, as I mentioned. But okay, that looks all good. I think I'll make sense on how this works. The only issue is now, can we find the replacement? So I'm going to open the other one, order some parts from DigiKey. We'll remove all these components, clean them up, and hopefully we can fix it. And in order to show you the close-up of those modules, I'm going to use this Andostar microscope. I've had this for a few months. I have to say I'm quite impressed with it. I've been using it a lot around the lab. Aside from the fact that it has a very nice setup and it has a good working distance here, you can see I have an object here underneath. It has a reasonably fast frame rate, but it also has an HDMI output, and you can record things into a video format directly on the unit. But the HDMI out simultaneously shows it on this screen, and another screen allows me to do a video capture. Yeah, so I've been using it. I'm going to leave a little link there for you to take a look at it if you want, but for something quickly around the lab, I think this is a good option if you're interested. So let's go ahead and take a look at this under the microscope. This is now the good TR module, and you can see the resistors are quite nice and intact. And indeed, this is a fairly close spacing between them. And here we can see all the values, so it should be easy to order the sizes and order the values directly from DigiKey. It's not too difficult to now fix this now that we know a good one. It's interesting to see some tiny matching networks that has been embedded in there just to make sure that the capacitances associated with these resistors are properly absorbed, creating a well-behaved impedance. And here's the AC blocking capacitor, you can see, or DC blocking capacitor here. You can see these resistors on the test port and the resistors on the reference port are not actually the same. So indeed the resistances are all different, and that's part of the equation, is how this bridge is used to extract the values you're looking for, the unknown impedance connected to this port at the bottom. So I think it looks good overall. Let's take a look and see what happened to the TR module I cleaned up. I had to do quite a bit of work on it to get rid of the board as it was quite damaged. And here's the area that I was referring to. You can see that I had to carve out quite a bit of this PCB material. There's a bit of a well here now because the top layer was completely destroyed. And that top layer characteristic impedance has totally changed. It can even become resistive and totally change the way this response of these resistors were as a substrate that sits underneath it. The traces are all gone here. The pads are of course all gone. But we should hopefully be able to assemble the same structure we saw in this area. These pads are okay. There's some burn section here, but it's okay. This doesn't seem to be coming off. I don't want to dig too much into this board. The connections appear to be intact as well. So yeah, the only other thing to do is really to try and replace this and replicate what's on the other module, and hopefully the response would improve. So I went ahead and replaced those resistors the best that I could. Now you have to keep in mind that these resistors are actually floating in air because the substrate underneath them is all gone. So soldering all of these things simultaneously, these are tiny. We can see by comparison the gap between these two resistors is very small. In fact, this branch and this branch are not connected to each other, so they do have to be separate. So it's a little bit difficult to put together, but we can do some basic measurements on this and compare it with the original one, which is over there. And I can go ahead and measure the resistance between them using my Keithley the EQ6510, which I've also done a review of. Let's go and measure it, see what it looks like. So I will first measure between two of the resistive points from the original board. So here's from between the reference and test points, 248.6 ohms, and I'm going to measure now on the circuit that I have modified, 248.8 ohms. So the resistances are definitely correct. That's a fairly complex resistive network in the Wheatstone Bridge there, so I think the resistances are good. Now this of course doesn't tell us about the high frequency response of these paths and all the coupling capacitance and all the extra stray components that I have introduced as a result of my modification, but this still tells us something about how this circuit works, which I think is a positive step forward. So even though we measure the resistance of this repair that we've done, I want to measure the response from the port to the return path, and this is our coupled path. This basically will capture this response across frequency. Well, I can measure it using a network analyzer. This is the Rod and Short ZNL6, which I'm doing the review on. It is the successor to the ZNLE, which is at the top, which I've already done a review on. This is a fantastic 3-in-1 instrument we're going to take a look at later. So I'm going to measure the S parameters from here to here, and this includes the resistive network. This is on the good port that was already in the instrument. Then I'm going to compare it to the one that I repaired. So let me set that up. And so here's the response, and you can see the S21 and S12 through that path is really flat up to 6 gigahertz, which is above the frequency that this instrument is rated for anyway, but it looks quite good on the original port, on the working one. So I'm going to save this to memory, I'm going to swap it out, and then we can compare them essentially one-on-one on top of each other and see if there are any differences. Okay, so here is the repaired one, and certainly the S21 and S12 look very good. You can barely see the differences between the original line and the one that I have repaired. If I look at the S11, there are some differences indeed. You can see that the impedance is certainly not exactly the same, and we can't really expect them to be the same because these changes were just done manually on a substrate that was quite a bit modified. So another question is, are these differences significant enough to cause a problem? Well, even if we can get the S11 of the instrument to be perfect, the factory settings have changed, but that repair was still necessary no matter what. So I think the next step is really to put this back into the unit and test it. Although I know this looks good, either way I would say this repair is quite good so far. So here's the instrument all back together. Now to test to make sure that the port 1 is still working correctly and that it can be factory calibrated back to its original specification, we can run a thorough self-test. And the self-test of the instrument is really extensive, and it includes all kind of measurements as well as measurements between the ports and looking at the returns on each port, receivers on each port, and transmitters. So it's really quite nice to see that this is included in the unit. And I ran the test, and you can see everything passes. So the instrument basically passes all of the factory self-test. So the next thing to do is to run a proper calibration on it and measure something to make sure that the responses look good, the channels can be balanced indeed, and then a factory calibration at the end should bring it back to the way it's supposed to be. So let's give that a try. And just to do a quick performance verification here, we're going to measure this 8445 automatic pre-selector, which I upgraded to an adjustable one in one of my previous videos. This is an ultra high quality yeek filter that's tunable, so we can measure that. It's got two different modes of operation. We can put it into low band for the moment, and when you put it in high band, you can adjust it using these high band adjustment knob. At the same time, I've already calibrated the whole thing using the eCal, so we should be able to go ahead and see what the instrument reports. And here's the measurement result when the filter is in a low pass mode, and you can see that it has a very nice response and a huge drop here. It's a multi-stage filter here, and the insertion loss, let's say at 1.3 gigahertz, is about 1.2 dB, which is what we expect from this filter. Now we can also put it into the other mode, which is the yeek filter mode. There it is, and here now I can adjust the filter center frequency, and you can see some of the other characteristics of the filter, like this notch over here. Remember, these things are way down. This is 40 dB down, and for the purposes of a pre-selector, this is quite good. Let's put it somewhere, let's say over here. We can do some additional measurement here. I can do a marker search. I can do a peak marker search. I can go ahead and turn the search range. Actually, no, what I want to do, I want to turn the tracking on. I can also measure the bandwidth of the filter. Over here, you can see the bandwidth is about 24 megahertz, which is about correct. It can go down, and at lower frequencies, the bandwidth is about 13 gigahertz. Actually, it's measuring the wrong place. There we go. 24, yeah, about 20 to 25 gigahertz is the correct bandwidth for this kind of pre-selector. So it looks good. It seems to be working, and I can also measure the return loss. S11, for instance. You can see that we have a notch exactly where we expect the filter to be. That's also, of course, correct, because that's where the filter is operating. Outside of that range, the filter is returning and reflecting all the power back. I'm also going to go ahead and measure S11. I'm going to disconnect the cable. The measurement plane in this case is at the end of the cable. So by removing the cable, I should see a very good return loss, because everything will bounce back at the end of the cable. We're going to have essentially an ideal open. Remove that. There we go. And you can see that we have an excellent S11 after calibration when I remove the cable. Here's the end of the cable. And if I bring my finger here, you can see that by touching the end of the cable, I don't recommend you to necessarily do this. You can see that I can absorb the power into my finger. There you go. Looks good. And there you have it. I hope you enjoyed this repair. Of course, with the repair of the TR module, this instrument still has to go through some kind of a factory calibration in order to match the TR module with the default plane, measurement plane at the connector. That still needs to be done. And of course, this hasn't gone through that calibration process, but as you can see, the unit is fully functional. And when we perform our own calibration at a different measurement plane, everything works fine. So with the new hard drive and all the modifications, I think this thing can now be calibrated and put back into service. And thanks again to Altes for providing this instrument for repair. I hope that you learned something. I'll see you next time.